Hey everyone, welcome to lesson 21. Let's start with this warm up. What is the hardest or most challenging thing that you have ever done? What did you do to overcome or accomplish whatever that challenge or obstacle was? Thank you for sharing. All right, let's get started with class. Remember our expectations, no matter what version of school we are in, to be safe, responsible, respectful, prepared, and here. We are on the live lesson. So this is either for Group A was on Tuesday this week, for Group B was on Wednesday this week, and the virtual group, this was all virtual and asynchronous this week. There was no live lesson. So virtual folks, you should be here for sure right now. If you missed your Group A or Group B live lesson, you also need to be here completing this. We are talking about how energy is conserved in a chemical reaction. And this fits in nicely with the 4 assignments we had this week. The preview, hopefully you've already done. The chemical reactions, energy and chemical reactions text analysis. There's an Edpuddle about endothermic and exothermic reactions, as well as our mental health check, which is an empathy assignment. So we're going to get into our work today and start with this. So stress check, where are we at today? How is on the scale from 1 to 10? How ready are you to work, and where is your mental state? All right. Well, I hope you're ready to dig into this. This was a really fun lesson in person, and I'm sad and bummed that some of y'all didn't get to do it, but I'm glad you're here now. So let's start with this. Last week when we talked about collision theories, the idea that particles are always moving around, they're always bumping into each other, we discussed that there's 2 things that need to line up and happen for one of those collisions to be productive and result in an actual chemical reaction. What are those 2 things? So the 2 things that we discussed is that those particles that are moving around and bumping into each other, if they're not going fast enough, if they don't have enough energy, then there's not enough energy to break or kickstart whatever reaction is going to happen, and they'll just bounce off of each other. Similarly, is if the molecules are not facing the correct direction or they don't have the right orientation, they'll bounce off and nothing will happen. So the 2 things that have to come together for a chemical reaction to occur, in what collision theory discusses, is that the reactants must have enough energy, enough speed when they hit each other, and they must be oriented or facing the right direction. This is important, especially when we talk about today with these endothermic and exothermic reactions, is the idea that every chemical reaction does need at least a little bit of energy to get kick-started. This is called activation energy. And we're going to see it in these graphs that we're going to be looking at later. We are going, you'll see that each of them has a little bit of energy that it needs. That's what this hill overcoming is. All right, so now let's recall what happened in an experiment that we did at the beginning of the year. Now, unfortunately, we didn't get to do it in person because of COVID, but this was something that we did discuss in our classes. This was the burning a Cheeto, the flaming Cheeto lab. So I want you to start by telling me what happens when we burn a Cheeto. And then the second thing I want you to think about and answer for me is, what did we learn about energy from this experiment? So I'm going to play this for you while you get started. All right, so at this point, make sure you answer what happened, what is happening right here as we burn this Cheeto. You can describe some stuff we talked about last week, like if it's a chemical reaction or a physical change, how do you know? And then the second question is, what do we learn about energy and how energy works from this lab? All right, so what we saw happening there is that we saw a chemical change when we burned that Cheeto. There were two or three actual pieces of evidence that might have told us that. One, we see energy being given off in the form of light and heat. That's literally the heat from the Cheeto is going into this can. It was so hot that it was causing that can to vibrate. The can has some water in it and a thermometer. And what we saw happening is the temperature change of the water in the can as the Cheeto burned. We also see that the Cheeto's color changes because we have a new substance. And also, if you've ever actually done this, it is a stinky. So that smell tells us that some sort of molecule of gas was created that wasn't there before. Now, what we learned about energy is the important thing. So clearly there's energy in this Cheeto because when you burn this Cheeto, that energy is being released in the form of light and heat. And that was the big thing that we took away from this whole experiment is that when you burn a Cheeto, you get thermal, which is heat, and radiant, which is light energy that is released. It was the combustion of that Cheeto that caused that to happen. Combustion is a fancy name for burning. Now, what we then thought about, if you pull back in that brain of yours, is that we discovered or thought about how the fact that the energy that was released has to come from somewhere, and where it came from was stored chemical energy within the Cheeto. So this, again, makes even more sense because a Cheeto is primarily made of corn. Corn is a vegetable. Vegetables are made of things called carbohydrates, which are the energy source of living things. Inside those chemical bonds of those carbohydrates is tons of energy, and that's why we eat carbohydrates to give ourselves energy. That corn, in turn, it got its energy stored in those chemical bonds from our friend the sun. The solar radiation reacted on the leaves of the corn to undergo a photosynthesis reaction, taking that solar energy and turning it into usable chemical energy in those carbohydrates. So the takeaway from this is that there's energy in everything, and that during chemical and physical changes, energy changes forms all of the time. But we need to think and remember that the energy may change forms, but it's there no matter what. So the law of conservation of energy states that energy cannot be created or destroyed, but it will change forms. And the total energy in the system will remain the same. So what we mean is that energy doesn't just appear, it doesn't just disappear. If it's in one form but not in that same form at the end, it's because it changed form to something else. And the total energy of the beginning and the end, the reactants and the products, will be the same. But you have to take into account that the form of that energy might have changed over the course of that reaction. All right, and that's essentially what these say right here. So what I'm going to have you do is open up this assignment. Unfortunately, you're going to have to rely on some of my descriptions because you can't do this in person. But you're going to open up this document and make a new copy. Make sure you put your name in it, and your document should look something like this. Oh, no, that isn't that one. Let's see. All right, so what we're going to do is I have done two reactions for you. And here, I'm going to pull it up for you all, my bad. I have two reactions. The first one is I took a little bit of sodium carbonate and calcium chloride. And what I did is there it is. And what I did is add a little bit of water to that and watch what happened. All right, so if you can see, this is what it looks like. We will be on the second slide, and you're writing some observations about what you see. And what I'm going to tell you is happening is that although all the materials in the water were room temperature, this substance right here that I'm touching is very, very hot. Okay, so write down your observations here. All right. So now for reaction number 2, what I took for reaction number 2, you'll go to the second one, is I took ammonium nitrate and a little bit of water. The ammonium nitrate started off as kind of solid pebbles. And you can see that it essentially became a clear liquid. But what happened with this is that, again, everything started at room temperature. This got ice cold. All right. So write those observations down now. All right. So to understand what exactly is happening, we need to understand the difference between these two types of reactions. So I'm not going to tell you which was which yet. You're going to figure this out on your own in a second. But one reaction we saw was called endothermic, and one reaction we saw was called exothermic. So both of these have this root word, therm or thermic, and that is always relating to temperature. Endo, in endothermic, endo kind of sounds like into, right? So heat into. So what happens in an endothermic bond is that energy is added into the reaction to break some bonds. And this makes sense. If you think about what would have to happen to break a pencil, I have to put energy, almost break it. I have to put energy into this pencil to break it. So in an endothermic reaction, energy is going into the reaction, endo, because we are breaking bonds. The opposite of that is called an exothermic reaction. Exothermic reactions lose energy. When they lose that energy, it's usually in the form of heat, and that's why that will always feel hot to us. Exothermic reactions release heat when they are making new bonds. All right, so there's some key differences between endothermic and exothermic. But both of them are still meeting this law of conservation of energy. Whatever energy was added can be accounted for in the products, or whatever energy is lost can be accounted for at the end as well. So like I said, endothermic reactions, or exothermic, are ones that lose or release energy. And we feel that as heat. So they're always going to be hot to the touch. Think of all the exothermic reactions you have seen. What results then is that your products have less energy than your reactants. So your reactants start with a certain amount of energy. Some of that energy gets lost. So the products end up having less than what you started with. And again, this is when you're making bonds. You're releasing energy when you're making these bonds. So to visualize that, this is an energy chart that kind of shows that. Again, our reactants, we have that little bit of energy that we need, that activation energy to get the reaction to start. But then energy is lost. That's kind of what's visualized here. So our products have less energy than our reactants. Endothermic is the flip of that. So endo, again, energy in. That takes in energy. And what that means is, to us, it's going to feel cool. The products end up having more energy than the reactants because there was energy that was added. And the difference in the energy amounts in the reactants and the products is accounted for whatever energy was added to this. And again, remember, that is for breaking bonds. It takes energy to break a bond. Again, here is the visualization of this one. Reactants and products. The products have more energy than the reactants because we added energy to it. All right, so let's go back, take a look at your notice and wonder chart, and let's go back to reaction 1. This is the one that I told you looks kind of milky white, and it got hot. I want you to tell me, fill out the rest of the chart saying what type of reaction occurred and how do we know? All right, so that was, if it got hot, that means it is an exothermic reaction. That's how we know an exothermic reaction is happening. So now the second piece of this is I want you to explain what is happening in an exothermic reaction like that one, or like you see on your screen, what is happening to the molecules? And I want you to think specifically about making or breaking bonds. So what can you predict is happening with the molecules in an exothermic chemical reaction? So what you should have thought of is that that we are clearly making new bonds because energy is being released. And energy is released in an exothermic reaction when new bonds are made. So now go to reaction 2. This is the one that got really, really cold. It's pretty see-through now. It's like that is completely reacted or it has dissolved. So what type of reaction occurred and how do you know? So this one definitely is an endothermic reaction. Because it got cold, that tells us that there is energy going into the reaction. Now, like that reaction or like this one shown here, what is going on with the molecules in this type of chemical reaction? Thinking about, again, are the bonds being broken or are they being made? So in an endothermic reaction, energy is going in because we got to break the bonds. All right. So the last thing to finish out your Notice and Wonder chart before you turn it in is I want you to add a couple of Notice and Wonder thoughts to this last one. You're then going to go to Google Classroom. You're going to find Notice and Wonder Chart Lesson 21. You're going to add it from Google Classroom since you've already done it, and then submit it and turn it in, and I'll have it. All right. So to finish out class today, we're going to do a couple of exit slips. So I want you to tell me which graph or which second half of the graph would represent this reaction, a reaction where products have more energy than reactants. Awesome. So if it has more energy, the products have more energy than the reactants, the products would be up here higher. This is showing an endothermic reaction where we added energy. All right, what about this one? One that is hot to the touch. All right, that means that it has lost energy, so our products are going to have less energy than our reactants. That was an exothermic reaction. A reaction where more bonds are made than broken. Remembering that made, when you make them, it releases energy. So what is that going to look like? Yep, another exothermic energy diagram. And our last one, a reaction where energy is added. So what do we think? Right, there it is. Okay, so I'm sorry that we didn't get to do the lab in person and you had to rely on me just telling you what's going on. But I think that we hopefully still got the ideas that we needed from this, and our understanding about endo and exothermic reactions is good. So what I need from you is to finish out 53 and 54 from earlier in the week if you've not done that first. And then the two big things is to work on the post-lesson assignments. Number 55 is an Ed puzzle reviewing those two types of reactions we just discussed. And then 56 is a mental health check where we are practicing our skills in empathy. All right, I will see you guys next week. Have a wonderful Derby weekend and take care. Bye.